We are in Chapter 4, Exponential and Logarithmic Functions. Section 4.1 is Exponential Functions and Continuous Compounding. An exponential function is of the form f of x equals a to the x, where a is greater than 0 and not equal to 1. The domain for an exponential function is all real numbers, and you can see that in both of these graphs that are given. And then our range, if you notice the graphs are only above the x-axis, which is going to mean that it is going to be from 0 to infinity. And then it also has an y-intercept, which is going to be at a point called 0, 1. The first one that we have is where a is greater than 1, and the second graph is where a is a fraction between 0 and 1. The first one is also called exponential growth, and we see that a lot in business. We also see a lot of exponential decay, which is that second graph that we have. The rules for exponent numbers are summarized below. This is very important to review. This should have been covered back in an Algebra 1 or Algebra 2 course. And this is exponent rules. And it says if a and b are positive numbers and x and y are any real number, then, and these are all different rules that we need to look at. If you have an exponent, b to the x times b to the y, you can add those exponents together. When you are subtracting, that's the same as division, with the bases being written separately. When you have exponents right next to each other, that would be multiplying. Likewise, if you have two bases, you can take that exponent and put it on both of those values in the parentheses if you're multiplying or if you're dividing. For b not equal to 1, b to the x equals b to the y, if and only if x is equal to y. The first example says, evaluate the given expressions. Answers should not contain any negative or rational exponents. This word rational means fraction. And so if you ever have a fraction exponent, then you need to rewrite it. And so if you were to have something like b to the m over n, this is the same thing as saying b to the m power with the nth root. Likewise, it says no negative exponents. And if you ever have b to any kind of negative exponent, that means it needs to be rewritten as 1 over b to the positive exponent n. Part A says 3 to the second to the 5 over 2. Since those exponents are right next to each other, and looking at our rules right above, this means that we are going to multiply our exponents together. And if you want, you can put a 1 underneath your 2, and you can realize you can cross-cancel those 2's. And now you're just left over with 3 to the 5th. If it's asking you to leave it in exponential form, that would be 3 to the 5th. If it wants it as a number, you can go ahead and use your calculator and do 3. You have a little caret button, and then type 5. And that's telling it 3 to the 5th, and you should get 243. So definitely try that on your calculator. The next example says 3 to the 1.2 times 3 to the 2.7 divided by 3 to the 4.1. And the numerator and all the bases in the numerator and the denominator are 3. And I'm going to go ahead and look at the numerator first. And since I have bases and they each have an exponent, looking at the exponent rules right above, I'm going to add together 1.2 and 2.7, and that's going to equal 3.9. And then dividing by, I'm going to keep my base the same, so it's 3 to the 4.1. And I can combine these together too because they have the same base. I would subtract, and I would do 3.9, it's always the top exponent, minus the bottom. So 3 to the 3.9 minus 4.1 is going to be negative 0.2. And we can rewrite this as a fraction and say this is going to be 3 to the negative 1/5. And we said no negative exponents and also no rational exponents. So I'm going to go ahead and move this to the denominator and say this is 3 to the positive 1/5. And again, we cannot leave this with a rational exponent. And so we're going to keep it as 3 to the first, or just 3. And then that root is going to be the 5th root. Part C says negative 2x to the negative third times 3x to the 2/3. Those numbers that are out in front of the x's just get multiplied like normal, and negative 2 times 3 would be negative 6. And then your base is x, and we have x to the negative third and x to the 2/3. And with those, we're going to have to add them. So we have negative 3 plus 2/3. In order to add these, I am going to have to get a common denominator. I'm going to go ahead and do my fraction work up here. So I have negative 3 over 1 plus 2 over 3. So I'm going to go ahead and get a common denominator and multiply that first fraction by 3 over 3. And so this is going to be negative 9 over 3 plus 2 over 3, which will equal, so we have negative 6x to the negative 7/3. And again, we cannot have a negative or a rational exponent. So I'm going to go ahead and move that to the denominator. The negative 6, though, stays in the numerator. That does not move because it does not have a negative exponent. And so this is x to the positive 7/3. And then rewriting this without that rational or fraction exponent, we're going to have negative 6 over, and it's x to the 7th. The top number stays with it, and that bottom number tells you the root that we would have, which is the third root. The next one that we have says x to the third, y to the negative second, z to the fourth, all raised to the 1/6. First thing to note is that the bases are all different, so I cannot combine anything in the numerator or in the denominator because one has a base of x, another a base of y, and another one has a base of z. However, I do have a 1/6 outside, and I can go ahead and put that on each of those bases that we have inside the parentheses. And to do that, I'm going to multiply. So we're going to have x to the third times 1 over 6, y to the negative second times 1 over 6, all over z to the fourth times 1 over 6. Simplifying our fractions, we have x to the 3 over 6, or 1/2, reducing that, y to the negative 2 over 6, or negative 1/3, and then z to the 4 over 6, or simplifying it to be 2/3. From here, I note that my y has a negative exponent, and this I can move to the denominator. So this becomes x to the 1/2 all over y to the positive 1/3 and z to the positive 2/3. From here, x to the 1/2 would be the square root of x over, and I have the cube root of y times, and I have the cube root of z squared. This answer is fine. However, I can combine the two roots that I have in the denominator because they are the same. They're both the cube root. So if you wanted to, you can simplify this to being the square root of x and the cube root of all of that together, which is y z squared. On the next page, it is the future value of an investment. And so for this, we have compounded interest. It says if $P are invested at a yearly interest rate R, compounded in times per year for T years, the compounded amount in the account after T years is given by A equals P times 1 plus R over N raised to the N times T. And then continuously compounded is going to be if a deposit is invested at an interest rate R, compounded continuously for T years. The compounded amount is given as A equals P E to the RT. E is also a button that should be on your calculator. You need to look for that. Now this word compounded is the amount of times that the interest is put back into the account. And so when we have N compoundings, which was what our first equation is, that value of N is going to vary depending on the word problem that we are given. So if it has N is the number of compoundings per year, we're going to go ahead and add that in over here on the side. So N is going to be our number of compoundings per year. Some of the common words that we will see in word problems will be that it will be compounded annually. And annually means that N would be equal to 1. We also have semi-annually. And semi-annually means twice a year, so N would be equal to 2. Another common one that we have is quarterly, and that usually happens with a lot of the banks. So quarterly, and that would be where n is equal to 4. Another one that we usually see in problems is going to be monthly, which n is equal to 12. And another one that you might see is daily. And usually it will say the daily is not including leap year, so it's 365. I'm going to leave some space there, or we have some space on the side. If you ever see any different ones in word problems, make sure to add them in. That way you have a running total of all these different words that could show up. So the next example, suppose that we have $5,000 is invested at an annual interest rate of 10%. Compute the future value of the investment after 8 years if the interest is compounded, and it says to round to the nearest cent. So we have $5,000 and it's invested at an annual interest rate of 10%. Whenever we have a rate, we need to express them as a decimal. So we can add this up here that rate needs to be expressed as a decimal. And our rate here is 10%, so rewriting this as a decimal, we would have 0.10. And then it says to compute the future value of the investment after 8 years, so that would be our T. And it says if the interest is compounded, and we have different parts. So part A says annually, semi-annually, daily, not a leap year, and continuously. And then it also tells us to round to the nearest cent, which is what we normally do with dealing with money. So the first one that we have says it's compounded annually. And since it says annually, we know that n is equal to 1. We also have been given a lot of information here. This 0.10 is our rate, or R. 8 years would be our T. So T is equal to 8. And this amount that we have is our principal, which is our P. So our formula from up above is A equals, and it's P times 1 plus R over N raised to the N times T. And at this point, we have everything. We have P, we have R, we have N, and we also have T. So substituting all of those values in, we can figure out our future value for this. So we have $5,000. And then it's 1 plus R, our rate written as a decimal is 0.10, divided by N, which is 1, raised to the 1 times T. T again is 8 years. And so I usually will substitute this all into my calculator. When I do, I'll get a total of $10,717.94. The second part, part B, is the same thing, however, now compounded twice, meaning that they're going to put interest into our account twice a year instead of just once a year. So we should actually, in the end, have more money in our account. The formula is written up above, so I'm going to go ahead and now substitute in all the numbers that we know. We know P is equal to 5,000, that's our principal. 1 plus 0.10 divided by 2, and this is going to be 2 times 8. And if you want, you could put that in as 16 on your calculator. And when we do this, we get $10,914.37. So it's a little bit more, almost $200 more in our account after those 8 years. The next problem that we have is daily. It does say not leap year. It's usually assumed, so 365. And we're going to go ahead, and the formula is still up here, and I'm going to substitute this in for N. Everything else is staying the same, so it's still $5,000 principal. Our interest rate is still 10%. This time we're going to be dividing by 365 since that is our N. And then our exponent's going to be 365 times 8. It's a big number. You want to multiply that out first or put it in parentheses if you're having issues getting the correct answers. When you do, this again is now every day. They put a little bit of that interest into your account, and so you should have even more money in your account after those 8 years, and we do. We have $11,126.49. And then continuously compoundings is a different formula that we have up above, and it's A equals P E to the RT. And so on this, we still have P is 5,000. Our rate is still 0.10 and T is still 8. E is going to be a button that's on your calculator. And depending on the calculator that you're using, you need to look for that. If you cannot find it, definitely let me know. So we have 5,000 E. Our rate was still 0.10 and our time is 8. So we end up with $11,127.70. And that is our most amount of money that we have in our account after our 8 years. The next formulas that we have are the present value of an investment. The present value, P of T, of an investment, A, accumulates at the annual interest rate, R, compounded in times per year over a term of T years, is given by P of T equals A times 1 plus R over N to the negative NT. And then it says if the interest is compounded continuously at the same annual rate R over the term of T years, the present value is given as P of T equals A e to the negative R times T. So A, the capital A that we have in there, is how much you will need after time T. So this is how much you will need after time, and we use a capital T. So the next example says Faye is about to enter college. When she graduates 4 years from now, she wants to take a trip to Europe that she estimates will cost $5,000. How much should she invest now at 7% to have enough for the trip if interest is compounded? And we have two parts. Part A is quarterly and part B is continuously. And so for quarterly, I'm going to go ahead and copy down the formula that we have, the first one. And this is P of T is equal to A times 1 plus R over N raised to the negative N times T. And so the amount that she has, that she's expecting it to cost, is our $5,000. And so that's our A. That's how much she needs to have. And then our interest rate here is 0.07. I'm expressing that as a decimal. And she has to wait 4 years until she's done with college in order to go. And so this is our T. And then it also tells us that it's being compounded quarterly. So N is equal to 4. So going ahead and figuring this out, we're going to have A is 5,000. We have 1 plus R, which is 0.07, over N. N is 4, to the negative N times T, so 4 times 4 years. And working this out, we get $3,788.08. So for Faye to have enough to go to Europe when she's done with college, she needs to put into an investment $3,788.08 to guarantee that she should have $5,000 as long as this bank that she's investing in is going to have a 7% interest rate compounded quarterly. Now, if she goes to a different bank that has it continuously compounded, this is going to be a different story. So for continuously compounded, up above, you can see that we have a different formula. So our formula for this one, and go ahead and copy it down, is P of T equals A e to the negative R capital T. Our A is $5,000, still is what she needs for the trip. E to the negative rate is 0.7. And T is still the 4 years. So going ahead and entering this in on our calculator, we get $3,778.92. So she went with this bank instead and has continuously compoundings, then she doesn't need to invest in as much at this time because it's compounded more often. The next section we have is 4.2, which is logarithmic functions. A logarithmic function says if a is greater than 0 and a is not equal to 1, then the logarithmic function of base a is defined by f of x equals log base a of x. We have some rules down here. There are definitely some review that we probably need to go back and look at. First one says log base b of 1 is equal to 0. The second one says log base b of b is equal to 1. And then we have log base b of b to the x is just equal to x. And then it says for number 4, log base b of x is equal to log base b of y, if and only if x is equal to y. So as long as those bases are the same, then x would be equal to y. Number 5, 6, and 7 are dealing with converting and rewriting these and expanding and condensing logarithms. So the first one says log base b of u to the v is equal to log base b of u plus log base b of v. Number 6 says log base b of u divided by v is equal to log base b of u minus log base b of v. And number 7 says log base b of u to the n is equal to n times log base b of u. The graph of a logarithmic function is on the right, and it is actually an inverse of our exponential function. And so if you note on here, our domain is going to be from 0 to infinity. Our range is going to be from negative infinity to infinity. And then instead of having a y-intercept, which is what we had on our exponential, we actually have an x-intercept, and those values switched. So our x-intercept is going to be at 1, 0. The next example right below this says use logarithmic rules to expand and simplify the following expression. And we have log base 7 of 49x to the 5th divided by 5y to the 7th. So we're going to go ahead and use these rules that we have up above. So make sure you keep an eye on those. First thing that we can do is, since we are dividing, I can rewrite this as log base 7 of our numerator, which is 49x to the 5th, minus log base 7 of our denominator, which is 5y to the 7th. From here, I can expand this since we are multiplying 49 times x to the 5th and 5 times y to the 7th. And rewrite this as log base 7 of 49 plus log base 7 of x to the 5th minus, I'm going to put this in parentheses since we are expanding this whole denominator here, log base 7 of 5 plus log base 7 of y to the 7th power. And really quick with the directions here, it does say expand, and that expanding means it should be getting longer, and it is. The next thing I'm going to do is I can simplify this. 49 is the same as 7 squared, so I'm going to go ahead and write that as log base 7 of 7 squared. And the next one that I have is plus, and I have log base 7 of x to the 5th, and that 5 I can actually take out and bring in the front, and that's by that last log rule, rule 7 up above. And so we have 5 times log base 7 of x. I'm going to distribute my negative here to both of these terms, and I have minus log base 7 of 5 minus, and again we can take this exponent and bring it out in front, so minus 7 of log base 7 of y. The next thing that I am able to do is I'm able to simplify this first expression, and this, if you look back at your rules and you look at the third rule that we have, it says log base b of b to the x is just equal to x, so this is just going to be equal to 2. So we have 2 plus 5 times log base 7 of x minus log base 7 of 5 minus 7 log base 7 of y. And from here we cannot simplify anymore. We have no more exponents, and we also have expanded this completely. Right below this is a change of base formula. If you remember from logarithmic functions, you can only use a calculator if it's log base 10 or log base e. So if we have a common logarithm or if we have a natural logarithmic function. So a change of base allows us to use a calculator for any base of a logarithmic function. So it says if x is a positive number and if a and b are positive real numbers, then log base a of x is equal to log base b of x over log base b of a. And it could be any value there. So remember, ln is going to be the same as log base e, and log is the same as log base 10. And this is our natural logarithm. And below that is our common logarithmic function. And so you can rewrite this as ln of x over ln of a, or log of x over log of a. Those are all equivalent. Right below that, a logarithmic function and exponent function are inverses of one another. And we saw that up above with the graphs and what happened with our x's and our y's, or our domains and ranges. And so in order to rewrite these, you can take something that's in logarithmic form and rewrite it in exponential form. And the way that I remember this is I take my log base b and I raise it to the x power, and this is equal to y. And that is what we have right up above. The inverse relationship also means that e to the ln of x is just equal to x, and ln of e to the x is equal to x for all x's. The natural base e is commonly used base. However, this holds true for all bases. So the next example that we have says solve each of the following equations for x. So I'm going to go ahead and use the property that we were looking at right up above, and I'm going to rewrite this in exponential form. And the reason why is because we're a lot more comfortable with exponential functions than we are with logarithmic functions. So I have 4 to the 1/2 is equal to x. And 4 to the 1/2 is the same thing as the square root of 4, which is equal to x, or just 2 is equal to x. Part B says log base x of 27 is equal to 3. So we're going to take our x, raise it to the third, we're writing this in exponential form, is going to be equal to 27. And you might be able to figure this out from here. If you cannot, your goal would be to rewrite 27 in terms of exponent 3, because our x is raised to the third power. And so that's the same as saying 3 to the third. And so this would mean that x is equal to 3. Right below this, we have properties of logarithmic functions. The logarithmic function f of x is equal to log base b of x with b greater than 0 and b not equal to 1 has the following properties. It's defined and continuous for all x greater than 0. The y-axis is a vertical asymptote. The x-intercept is at 1, 0, and there is no y-intercept. If b is greater than 1, then the limit as x approaches 0 from the right of log base b of x is equal to negative infinity, and the limit as x approaches positive infinity of our logarithmic function is going to be equal to infinity. And you can see that up above in our graph, and I'll go ahead and just sketch that really quick for a logarithmic function. And you can see as it goes off to the right, it's going off to positive infinity, and to the left, it's going down to negative infinity. And then it says if b is in between 0 and 1, then our logarithmic function, as we're approaching 0 on the right, is going up to positive infinity, and off to the, as x approaches positive infinity of our logarithmic function, it goes off to negative infinity. I'll go ahead and sketch what that would look like. And so again, you can see as the limit as it's approaching 0 on the right side, it's going up to positive infinity, and as the limit as x approaches positive infinity of our logarithmic function, it's going down to negative infinity. 5 says for all x greater than 0, the function is increasing or rising if b is greater than 1, and decreasing if it's between 0 and 1. So this is an increasing function. And over here, this is decreasing, kind of going with what we saw before. We have another box right below this that says doubling time. A quantity q of t is equal to q naught e to the kt. if k is greater than 0, doubles when t is equal to d, where d is equal to ln of 2 divided by k. So the example right below this says, how long will it take $5,000 to grow to $7,000 in an investment earning interest at an annual rate of 6% if it's compounded? And we have part A, which is quarterly, and B, which is continuously. So for part A, it says quarterly, so I'm going to go ahead and copy down our formula from before, which is P times 1 plus R divided by N raised to the NT. And since we have $5,000, this would be our principal, and it grows to $7,000. That's going to be our amount that we would have, which is A. It's earning an interest at 6%. Again, we talked about rewriting this as a decimal, and this would be our R. And it's compounded, and for here we have quarterly, so N would be equal to 4. It's asking for how long, so we need to figure out T. So we don't know what T is. So substituting in our values, we have A is 7,000, P is 5,000, 1 plus we have R, which is our rate, which was 0.06, N is 4, since it's quarterly, and then we have 4 times T, and T is the value that we do not know. Going ahead and simplifying this, I'm going to go ahead and zoom in. I'm going to divide both sides of my equation by 5,000. And so I have 7 over 5 is equal to, and I have 1 plus, and these are all numbers, and I can go ahead and substitute this in on my calculator. And when I do, I end up with 1.015. Suggestion would be not to round. If you have a longer decimal, is to leave it. So you don't have any kind of rounding errors and miss the problem because of a rounding error. And this is raised to the 4t as our power. From here, I need to solve this. And since I am solving for an exponent, I need to get that exponent from being an exponent to being down, out, and into the actual problem. In order to do that, I'm going to go ahead and take the natural log. And again, you could take any log that you would want. I'm choosing ln. And the reason why we use a logarithm for this is because we have an exponent that has a variable. And when I have a log, I can move that exponent out in front of our logarithmic function. And I have ln of 7/5 equals 4t times ln of 1.015. And my whole goal is to solve for t, so I'm going to divide both sides by 4 ln of 1.015. So I'm going to end up with t is equal to ln of 7/5 divided by 4 times ln of 1.015. And now from here, I'm going to substitute this whole thing in on my calculator. Make sure you have parentheses around the 7/5 and also around the 1.015 so it knows where to take the logarithm from. When I do, I'm going to get 5.65, and we're measuring this in years. Part B, we're going to go ahead and circle, and we will work on that one together in class. The next example right below this says if Hubert invests $1,000 at 8% annual interest compounded continuously, how long does it take for his investment to double? And we do have up above a box that says doubling time, and we can use that to make this go a little bit faster. Doubling time says that we are going to take ln of 2 divided by k. And so I'm going to go ahead and put down d for our doubling time is equal to ln of 2 divided by k. If you did not want to do this, there is another way to do the problem. And if you have questions about it, definitely reach out and ask. And so going ahead and looking at this, it says if Hubert invests $1,000 at 8% annual interest and compounded continuously, how long does it take for the investment to double? So looking back up at our formula here, it says a quantity Q of t is equal to Q naught e to the kt. And again, this is continuously compounded. And it doubles when t is equal to d, where d is equal to ln of 2 divided by k. And if you see k in here is going to be our rate that we would have. And for this, we have ln of 2 divided by k, which is 0.08, which is our annual interest rate here, which again, rewriting this as a decimal. And using our calculator from here, we get 8.66 years. Section 4.3 is differentiation of exponential and logarithmic functions. So 4.1 and 4.2 was a review of exponential and logarithmic functions, and this is now getting into the calculus part of it. So definitely if you're struggling with some of the review topics in 4.1 and 4.2 and you need some extra help, make sure you reach out either to me or the TMARC. And this is now moving into the calculus part of it. So this says exponential and logarithmic functions are extremely useful, especially in business. In order to analyze these types of models, we will need to be able to differentiate them. So we have some formulas that we need to have memorized. First one is derivatives of exponential functions, and the derivative of e to the x is equal to e to the x, so that's an easy one to remember. And the derivative of b to the x is going to be ln of b times b to the x. Likewise, right below this is the same thing, however, when we have to use the chain rule. So this is the derivative of a more complex function. Now we don't have just e to the x, we have e to a function like x squared plus 7. And so in order to do this, we still have e to the g of x, but then we have to take the derivative of our inside function, and in this case it's our exponent. Likewise, if we have the derivative of b to the g of x, we're going to have ln of b times b to the x, which is what we had up above, times the derivative of g. So we have some examples right below this. Try some of them together, and then we'll leave some of them to do in class. So the first one is finding the derivative of each of these functions. A says y equals 6e to the x, so our derivative is dy dx. 6 is just a constant, so that would stay the same. And the derivative of e to the x from up above is just going to stay e to the x. Part B says f of x equals 4 to the x. So finding our derivative, I'm going to go ahead and write f prime of x equals, and we have the derivative of b to the x is just ln of b. And so we have ln of 4, and then it's times 4 to the x, or b to the x, like we have up above. There's not any simplifying. You cannot multiply these together because we have 4 to the x, and ln of 4 you cannot combine. Part C is y equals 3 to the x times e to the x. So dy dx. And since this time we have two x variables in our problem, we need to use our product rule since we're multiplying them. So the first term we have is 3 to the x. And then we have to take the derivative of e to the x, which is just e to the x, plus our second term, which is e to the x, times the derivative of 3 to the x, which is 3. So from here, if you wanted to, you can factor out a 3 and an e to the x. And we're left over with 3e to the x times x plus 1. And this would be your derivative. Part D. F of x equals 5x to the third minus 2x divided by 3 to the x. So in order to do our derivative here, we are going to have to use the quotient rule. And so the quotient rule says the bottom times the derivative of the top, which is going to be 5x cubed minus 2x. Taking the derivative of that, we get 15x squared minus 2 minus the top, which is 5x cubed minus 2x, times the derivative of the bottom, which is going to become ln of 3 times 3 to the x, all divided by the denominator squared. So from here, if you notice, both of your terms have a 3 to the x, so you can cancel out the 3 to the x with one of the 3 x's down at the bottom. And we can't do much simplifying. We do end up with 15x squared minus 2. If you want, you can distribute your negative and your ln of 3. I'm going to leave this and just say ln of 3 times 5x cubed minus 2x. We can't combine anything else because of that logarithm, the ln of 3, divided by 3 to the x. If you get a different answer from this and you're simplifying a little bit more or a little differently, make sure you send a picture of what you have to my email and I can check and see if you did it correctly. E and F we are going to go ahead and circle and we will work on those together in class. Next we have rate of change of a function means to take the derivative of the function and evaluate the given value. So the example right below that says, suppose the cost in dollars to make 100 tables is given by C of X equals, this is 100,000 divided by 1 plus 100 e to the negative 0.3x. Find the marginal cost when 500 tables are sold. So since we're dealing with X hundreds of tables, we want to find our marginal cost, which is C prime of X. But when X is equal to 500 tables are sold, so X would be equal to 5, since we are dealing with this in terms of hundreds of tables. And so in order to find our marginal cost, we are going to have to take a derivative. So C prime of X is equal to, and we will have to use our quotient rule since we do have a fraction here. And so in order to do this, we have our denominator, which is 1 plus 100 e to the negative 0.3x times the derivative of the numerator. The derivative of the numerator is just 0, minus our numerator, which is 100,000, times the derivative of our denominator, which taking the derivative of 1, it's just 0. And then we have 100 times the derivative of e to the negative 0.3x is going to be negative 0.3 e to the negative 0.3x. And then this is all divided by our denominator squared. So from here we can clean this up a little bit. Multiplying our 100 times our negative 0.3 times our negative 100,000, we arrive at 3 million e to the negative 0.3x divided by our denominator squared, which is 1 plus 100 e to the negative 0.3x all squared. And this is our marginal cost function. However, we're asked to find the marginal cost when 500 tables are sold, so when X is equal to 5. So going ahead and substituting in 5 into our function. And careful because those are rather large numbers, and double checking this to make sure you entered everything in correctly. And working this out, I'm going to round 2 decimal places since we are dealing with money. We have $1,231.60. So the marginal cost when 500 tables are sold is going to be $1,231.60. Right below this, we have derivatives of logarithmic functions. And again, x has to be greater than 0 because our domain for a logarithmic function is positive or greater than 0. Derivative of ln of x is equal to 1 over x. And the derivative of log base b of x is going to be 1 over x times ln of b in the denominator. The next set of formulas that we have are derivatives of logarithmic functions with the chain rule, where g of x is greater than 0. Note that there is a typo, and please change this from ln of x to ln of g of x, and right below that, log of b of g of x. So the derivative of ln of g of x is equal to 1 over g of x times the derivative of g of x. And the derivative of log base b of g of x is equal to 1 over g of x times ln of b in the denominator times the derivative of g of x. Right below this it says example, find the derivative of each function. The first function that we have is log base 3 of x. And so to find our derivative, we're going to go and write f prime of x. And our derivative is going to be 1 over ln of 3 times x. Part B says find the derivative of f of x equals ln of 3x, and if it makes you feel more comfortable, you can put parentheses around the 3x. And we have ln of 3x, and for this we have f prime of x is equal to 1 over 3x times 3, which is going to simplify to, and again, 1 over 3 of x is because we use 1 over what it is we're taking our logarithmic function of, times the derivative of 3 to the x, which is 3. This is just going to simplify to 1 over x. On the next page we have C, and C says f of x equals ln of the square root of 2x minus 3. And again, remember the square root can be written as ln of 2x minus 3 raised to the 1/2. And so in order to find our derivative, we're going to write f prime of x, and this is going to be 1 over our function, which is the square root of 2x minus 3, times the derivative of the function, and I'm going to go ahead and look at the one that's written as 2x minus 3 to the 1/2, which requires us to use the chain rule. So we have 1/2 times 2x minus 3, subtracting 1 from our exponent to the negative 1/2, times the derivative of the inside function. Derivative of 2x minus 3 is just 2. From here we can simplify this. The 2 and the 1/2 will reduce out, and we end up with 1 over the square root of 2x minus 3. And then this part, which is 2x minus 3 raised to the negative 1/2, is going to move to the denominator and also becomes a square root. So we have the square root of 2x minus 3. And the square root of 2x minus 3 times the square root of 2x minus 3 just simplifies to 2x minus 3. Part D says y equals log base 4 of 5x plus 3x cubed. So our derivative, or I will write dy dx this time, is going to be equal to 1 over, and we have ln of our base, which is ln of 4, times what we're taking our log of, which is 5x plus 3x cubed, times the derivative of our inside function, which is going to be 5 plus 9x to the second. From here we can just clean this up a little bit, and we have 5 plus 9x to the second divided by ln of 4 times 5x plus 3x cubed. We have two more here. We have E and F, which we'll go ahead and circle, and we'll work on those ones together in class. The next example that we have says the total revenue received from the sale of X items is given by R of X equals 5 ln of 4x minus 1, while the total cost of producing X items is C of X equals 3x divided by 11. Find the following. The first one is asking for the marginal revenue, and since we are given the revenue function, we just need to find R prime of X, so taking that derivative. So R prime of X, which is our marginal revenue, is going to be, we have 5 times, so that 5 is a constant, would stay there, and we have ln of 4x minus 1. So we have 1 over, since it's ln, we just have 1 over our function that we have, which is 4x minus 1, times the derivative of 4x minus 1, which is just 4. So this simplifies to 20 divided by 4x minus 1. Part B says to find the profit function, which is P of X. And we know that P of X is equal to our revenue minus our cost. And we have our revenue function up above that was given to us, and we also have our cost function, which is also given to us. So our profit is going to be revenue, which is going to be 5 ln of 4x minus 1 minus our cost, which is 3x over 11. Can't simplify that at all, and we'll leave that just as that is. Part C says to find the marginal profit when x is equal to 10. So in order to find our marginal profit function, we need to take a derivative of our profit function that we have up above. And so the derivative of the first term that we have, which is 5 ln of 4x minus 1, that's just our derivative of our revenue function, which I'm going to go ahead and get from part A, which is 20 divided by 4x minus 1. And then the derivative of 3 over 11 times x is just going to be minus 3 over 11. And now we have to find the derivative, or our marginal profit, evaluated when x is 10. So going ahead and substituting in 10 for x and working this out, we arrive at 0.24, and again rounding 2 decimal places since we are dealing with money. This is telling us that our marginal profit after 10 items have been sold is 24 cents. So at least we're still making money off of this item. The next example that we have on the next page says Edgar is the manager of a manufacturing firm. He determines that D of P is equal to 5,000 E to the negative 0.02 P units of the company's product will be demanded or sold when the price is P dollars per unit. So D of P, another way to think of this, is our function of Q and our demand function. Part A says to find the elasticity of demand for this commodity. What values is P? Is the demand elastic, inelastic, or unit elastic? So the first thing we need to do is find the elasticity of the demand. So this is back from previous units. And so in order to do that, go back and look for your formula, and I'll write it down for us. It's going to be negative P divided by Q times dQ dP. And so from here, we need to find our derivative, dQ dP. And we also have negative P divided by Q, and Q is up above is 5,000 E to the negative 0.02 P times dQ dP, which is going to be 5,000 times taking the derivative of E to the negative 0.02 P, we have negative 0.02 times E to the negative 0.02 P. Going ahead and simplifying this, we arrive at 0.02 P. And we have, it's asking for the next question. So that is our elasticity of demand function that we would have. For what values of P is the demand elastic, inelastic, and we also have unit elasticity. So it is going to be unit elastic when E is equal to 1. And this is when it was unit elastic. So we can take our function that we have for E, which is 0.02 P, and set this equal to 1. Solving this, we get P is equal to 50. Second one that we have is when it is inelastic. When it's inelastic, we have E is less than 1. And so taking our function and solving this, which was 0.02 P, is less than 1, we arrive at our price would be less than 50. And elastic demand is when E is going to be greater than 1. And so again, solving this or using what we have up above, we arrive at P is going to be greater than 50. So our price would be in dollars. So I'm going to go ahead and say $50 is when we have unit elasticity. Inelastic would be when our demand or our price is going to be less than 50, and elastic would be when the price is greater than 50. So we have parts B and C that I'm going to go ahead and circle, and we'll finish up those two parts together in class.